See me now?
Yeah, we're good. Turn your volume.
I am muted. Interesting. Hang on, everybody. A little feedback this morning. Good morning. My fault. Little feedback there because I'm challenged this morning. It was a late night and a very early morning for me. Good morning, everybody. Today we are going to look at setting up a sample project and getting a few explanations. No PowerPoint this morning. What we'll do with this morning's session is it will be recorded. And then what I will do after we record it is I'm going to take this back and I have a framework of lessons that I'll put this together for you. So you'll have the recording, and then probably about the middle of next week, I'll break this down into either a PDF document or a rough series of PowerPoint slides that we'll upload to you. And then you will be able to go back and to look at that and review it. Okay, so a simple project to get our robot moving. We'll take the robot outside and we'll let you see how everything is going to work. And James is going to break this down right from getting into VS Code, okay, to getting started as you go along with it. All right. We started a new project team this morning. I've just been chatting with a couple of them online. So at this point in time, you know, we've been working on getting this robot built for you and doing a few other things, getting ready for our upcoming online challenge. So just remember also that if you're going to participate in the online challenge this year, that you need to be registered with Frank by the 14th of May. Once we do that, we're going to send out a lot more details to everyone that is registered. So I encourage you to participate in that if you can. For those of you from Asia, remember that we have the Asia Online Challenge, which will occur later in the summer, and you should have some details from WorldSkills Asia on that. So to get prepared for that, you're going to find a lot more resources that are coming out for you, a lot more samples that are coming out for you, just to help to support you to get ready for Shanghai 2021 with the VMX and the Titan platform. Okay. With that, I will pass this off to James, and he'll start to discuss the project. I'm not sure how long this is going to take today. We kept a very simple project, but we're going to give you a lot of explanations, show you how the robot works, and then let you mess around inside VS Code and coding, and we'll stay online to give you as much support as we can on that in case you have any questions going forward. All right, thank you very much, and I'll pass that over to the smart guy in the room.
Yeah. So today we're going over the programming for the robot. I already posted this project to our examples GitHub, where you can go and download it and basically run it right away if you have the robot built. But I'm also going to start the whole project from scratch here so that you guys can see how to do that in the general workflow that I do. So showing on the screen right now is a blank VS Code, and I'm going to start a project. So I have to open up the command window. So that I can create a project. So I can just type in, and here you have create a new project. You don't want to use the other ones. You want to make sure that you use WPI lib create a new project. This will open up the project generator. So first select the project type. I just want a template. and then we're doing Java, not C++. And I'm going to go into command robot. I don't want to use the other types of robot. So now I have to select the place to put the project into. I'm going to give the project a name. So what's the project name here?
Basic bot.
Basic bot. And then I need the team number. The team number corresponds to the team number shown from the Wi-Fi of the VMX. So you'll see WorldSkills dash 1234, which is the default. The team number would be 1234. So I'm going to put in 1234. This is required so that when we deploy to the VMX, it knows what target to look for and the correct address to target. I'm not doing simulation, so I'm not going to check that box. Generate project. And then I'm going to do this window. What it's going to do right off the bat is a build. The reason why it's doing this is it needs to cache all of the libraries onto your computer. And as you can see, my build was successful. I was able to cache everything like I want. One thing to note is that you must be connected to the internet whenever you do a build where caching is required. I'm going to close these windows. You'll see here on the left-hand panel, the project tree has been created. To verify that you're using the correct version, you should go to your, you can look in your settings.gradle, you can see that the year is set to 2020, which tells me that I'm using the correct version. I can also see in some other places where it actually shows 2020, and that's why you want to make sure you're using 2020 and not 2021. So we go to the source file here. You can see the source for the robot. It's just blank right now, as there is no code written for the robot right now. We're going to add to it. Let's start with the constants.java file. This way we can set all the constants for the robot electrically so that when we create our classes and everything, we can hook them up and it's all nice to go. All right. So we'll start by setting the CAN ID of the Titan. So by default, the CAN ID for the Titan is 42. Although if you changed it to something else, then you'd have to put that CAN ID in. So now we're going to focus just on the constants that relate to the drive base. There are two main subsystems that we're going to program here. There's the drive base, which is driving the robot around. And then there is the object management system, which would be the elevator. So we're going to have two sections of constants. So M0 is currently the right motor. So I'm going to put in here right motor. M1 is plugged into the back motor. And M3 is plugged into the left motor. And then I have to set up the encoder maps so that I have my correct distance for the encoder. When I call get distance, it will return the correct distance traveled by each motor. So first thing is wheel. So the Omni wheels are 100 millimeters, but if you were to measure it, they're a little bit bigger. So a better number would be, instead of 55, I think 51. Yeah, because they're 102 millimeters based on the spec sheet. And if you measure them, they're pretty close to 102 millimeters. So my radius is going to be 51 millimeters. Then I need encoder pulse. So what this is that on the back of the motor, there is an encoder, and every spin of the motor shaft results in 1,440 ticks of the encoder. So that's what I'm going to put there. And we need the gear ratio. As the wheels are mounted directly on the output shaft of the motor, there is no gear ratio as it's 1:1, but I'm still going to put it there in case we change it in the future. We just have to come here and change the ratio. Now, if we had a gear ratio, we actually have to calculate the difference in the amount of pulses based on the output. For example, on our elevator, we have a 2:1 gear ratio, which means the output shaft on the elevator will spin twice for the one spin of the motor on the encoder. So therefore, the amount of ticks would actually be double the value. So that's why we have to calculate that in this ratio.
A little pause here in a minute and let everybody get caught up in case they don't type quite as fast as you do, if they're following along.
So Derek would like me to give a little pause here so you guys can catch up. So at the end here, we have the actual constant that we're going to give to the encoder class when required. So this is the actual distance calculated per tip. So if we were to do this, every rotation of the wheel equals So that'd be 1,440 times whatever the distance per tick is here, and you have that distance in millimeters. The cool thing about VS Code is that you can already see that the map's done for you. If I hover over the constant, it can show me what my actual value is there. Give you a few more minutes to catch up, and then I will continue. All right. So as I said before, we have two subsystems. So we have the drive-based subsystem and then the elevator subsystem. So I'm going to create another set of constants to match the elevator constant. Okay. The motor for the elevator is plugged into M2 on the type. The servo on the elevator to control the differential of the clock is plugged into port 12 on the VMX. However, this corresponds to PWM 0. So I must use 0 and not 12. If I use 12, that's a different PWM location on the VMX. And then there is an encoder as well for the elevator, so we have to do the math again for that specific encoder. Radius. As our output is a belt pulley, that's what we're actually going to measure as the radius, not an output wheel. So the radius is going to be different. And the radius of the pulley is about 7.85 millimeters. So that's what we're going to use. Now, if you remember, the gear ratio for the encoder is 2:1. So here I'm going to put 2:1, and then this will calculate what I need. So if you remember that VS Code will calculate for us already. If I hover over the constant here, we can see it's 2,880. So that means that for every one turn of the motor shaft, or every one turn of the pulley, we've counted 2,880 ticks. So what I had the gear ratio wrong here. It's got to go the other way. And I don't want integer division to go to a double, as it won't work. So I add the 0.0 at the end to give me the proper division. I get my distance. We're now done with the constants class, and we can forget about it for the rest of this program. So what we're going to do now is create the subsystem code. But before we create the subsystem code so that I can use the Titan, we have to bring in some vendor libraries so that we can use those vendor libraries. What I'm going to do is first grab the JSON. So to do that, I'm going to go click on the extension here in the top right. I'm going to find Manage Vendor Libraries. I'm going to install a new library online. Paste in the vendor link for the Studica JSON and hit enter. And then we want to run a build so that we can cache the libraries to our computer. And you have to remember, you must be connected to the internet to cache the library. And then you can see when I click on the JSON that I'm using version 1.0.0. And then because we're also want to use the internal navx from the VMX, we also have to bring in that JSON library. So I'm going to run the same command again. Bring that in, run my build. And you can see now that I have the navx included. So now we can create the sub. There's an example subsystem in there right now, so but we're not going to use that. We're just going to ignore it. So let's create it. Right click on the subsystems folder, new file. We're going to call this new file drive base. Right. So first things first, we have to include the package. This is so that we can tie the class to the rest of the project. Oh, there's a cube. Do you want to attach the docs to that question?
Okay. So somebody's looking for the docs, we'll do that. You know, and just just a couple things. What we'll do is you're gonna have the video, but we'll set up a review next week as well, like I said, with the project structure, okay? So you gotta, a couple of things, think about it, like James is working in constants.java, all right? And that's gonna contain all the numbers that don't change and that are relevant to the whole robot, okay? So, that would do things like, the encoder's values or port values that don't change, okay? And they would correlate to things like the motor controller and so on, all right? So we'll break down what each section in that project structure works for and where you're going to store things for each subsystem on your robot.
Right, so to continue, we now have to create the class. So we want the subsystem base. This will allow us to create this as a subsystem for our command-based robot. So let's define a few of our instances first. Well, not instances, objects. So let's define the motor objects. Answer. So here I define my 3 objects for each motor. Then we have to define objects for each encoder. Then we also want to define our sensors for the drive base, which in this case is the NavX for now. And we're going to be sending some data to the shuffleboard. So I'm going to define the tab and the entries for the shuffleboard network table. So this defines a tab on the shuffleboard where we can put our values that relate to the subsystem. So what this does is it creates an area that will show my left encoder's value. And then I just set a default value, which is the second parameter, to 0. So if there is nothing being sent to that value, it will just display 0. And the last entry for our shuffleboard here is the value of the NavX yaw, so we can understand what angle that the robot is at. Next, because Java, we have to create a constructor for our class. And in this constructor, we will create the instances of our objects. So we want constants.tighten e, which is the first value, which tells us this object is connected to this tighten. Now we need to tell it what motor we're on. Constants dot and so this now creates the instances for our left, right, and back motor. So let's also create the instances for our encoders. So the first, if you look at the parameters required for the Titan quad encoder, we have the Titan, the encoder, and the distance per tick. So first off, we have to pass the specific motor that we're putting in, which is left motor. The encoder is the same, so constants.m3. And our distance per tick is going to be wheel distance. And I'm just going to copy this to save time. All right, so that defines all the encoders. And then, of course, last we have to define the instance of the NavX. So what I did was I said that I'm going to use the NavX, which is using the SPI port KMXP. This is used to configure internally to say, oh, I'm using my internal NavX and not an external SPI that can go to an external NavX if you have one outside of the one built into the VMX. Now we're just going to create some methods that we can manipulate the different objects on our drive base. What we have here is made a method that if I call this, I can set the speed of the left motor. Let's copy this to do for the other 3 motors. So we just have to change it to those values. Okay. So now we have a method that we can call if we want to set any of the motor speeds on the drive. Now what happens if we want to call all 3 motors at the same time? Well, we can create a method for that. Set drive. So here we have the speed required for each motor if we wanted to set them all at the same time. Now, because we have a 3-wheeled robot, we actually want to do a holonomic drive algorithm. So let's go over how we will implement that. So, drive. So this takes in the 3 axes of movement that we want on our robot. So we'll have double. Okay, so that's for the right wheel speed. And then we need one for the left wheel speed. Okay, so that's the general algorithm required to drive the robot in the X, Y, and Z. But we need to constrain the numbers so that it fits within the -1 to 1 outputs that are required for our motor system. So to do that, we'll create some constraints here. All right. And then lastly, we just need to output that to the motors. So this one. And there we have the easy algorithm to drive the robot based on an X, Y, or Z input. Add a comment here. Drive robot using oh. Now we need the encoder. Now that we're done with the drive system, we have to read the encoder values.
One out.
Zero. Now let's copy this for the other two encoders. Change this. All right. Can't spell it. Now we need to, for our PID algorithm for driving forward, we have to get the average distance based on our two front motors. That's it for the encoders. So now we just need to read our yaw movement. So public double here, yeah. So now we have to find a way to actually reset our sensors. So to do that, there's two methods that we're going to use. So public void reset encoders. This will reset our encoders to 0. So left. And then we want to reset our yaw to 0 as well. And last but not least, to finish out the drive base, we need to create our periodic loop to send our sensor data to the shuffleboard for us to view. So this will override the periodic loop for us to add information. The periodic loop is called once per robot cycle, which is about 20 milliseconds, which is very fast. Oh, I did that. And there you go. This subsystem is now complete. However, there's one thing we need to look at. The encoder distances here. If we were to start moving the motor, we would notice that one of the encoders is actually giving us a negative value. This is just based on the way that the motors are, the way they offset like this. That moving in this direction, moving in this direction, is actually the opposite direction. So the one's going to be counting in the wrong direction. In this case, it's going to be the right motor. So we have to invert the encoder for the right motor. So to do that, we're actually going to do it up where we initialize our encoder. So I'm going to call right encoder dot set reverse direction. This will internally reverse the direction of the count, and we don't have to do anything outside of it. Next thing is we want to create the a gamepad so that we can actually drag the robot around as well. But before we get to that, we're going to take a quick 5-minute break so I can rest my fingers.
Yeah, and just remember here that what James has currently been working on is he's just doing some subsystems. Okay, so those subsystems, remember, they're independent parts of the robot that are independently controlled. So a drive base, an object management system, okay, a gripper, an arm, a wrist. You design everything in a subsystem, okay, and this helps simplify things so that you don't have a really complex code, all right, when you're going to work on it. So that's what we're doing here. And as I said, we're going to break this down even further for you. So We try to keep everything into simple subsystems, okay, easier to troubleshoot and easier to go through in the command structure. Okay. All right, let's take a quick, you take a break? All right. Start with a summary of what you did.
Okay, everyone, we're back. So let's go over what we did. So we created the drive-based subsystem, initialized everything so that our robot will be able to drive around. So as we said, next thing we're going to do is create the classes for our Gamepad control. So I'm actually going to create a new folder. So I'm going to click on the Java folder here. I'm going to right-click New Folder. I'm going to call it Gamepad. Right. So the Gamepad requires two files. There'll be a constants file and then the actual operator instructions file. So the first thing will be the Gamepad Constants file. We're going to import our package to add it to the rest of the robot class. And then create the class. And there's So what I'm saying is that when I attach my controller to my computer, the control station software that we use has different port IDs for the different controllers plugged in. As we're only plugging in one controller, our port will be 0 because that's the first index. So I know I'm just going to put 0 as my USB index for that controller. I use a PS4 controller to drive around. However, the controller in the kit's a bit different. So the mapping of the joysticks may be a bit different, but you can go in and change that. I'm only going to define the buttons and joysticks that we will be using for this as their blocks, and we don't need all of them. Now, first I'm going to say PS4 map. All right, so this is all we need for the constants for our controller, because we won't be using any more than this. The left bumper, right bumper, and right trigger on the controller will be controlling our up-down movement of our elevator and the closing action of the differential claw. For our driving around, we only need 3 axes of movement. So we have the left analog stick that will act as our X and Y. And then the right analog X-axis will act as our rotational movement if we want to rotate. So now we actually have to create code that we can read the joystick values. So I'm going to right click on the gamepad, create a new file. We're going to call this OI, which stands for operator instructions. Add it to the package again. I'm going to create a joystick. So what I've done here is I've created the constructor for the class. And what I said is that this joystick object is connected to the drive USB port 0. Now we need some methods so that we can read the different values. I'm just going to copy and paste from our other code. So what this code does is that I'm going to read the right axis of my controller, and it will read that right axis, and then it applies a dead zone calculation of about 5%. So the reason we have the dead zone is not all controllers perfectly snap back to 0 on the joystick. So we could create a dead zone so that when it snaps back to its home location, if it's slightly off, it's still reporting 0 back to the controller. This reduces any drift. Right now I have it at 5%. Some people might extend it to 10%. It's up to you. You can adjust it. I'm going to copy this so I can create it for the other three axes. The other two axes that we're using. So it would be get right, get left. And then we have our left y-axis that we have to get. So that covers the three axes for driving our controller. But we also need to read our buttons. So this is a simple way to read the button. It just returns back a true or false, depending on if you're pushing it or not. So this gets our trigger and our bumper. And then of course we need one more button for our closing of the claw. So I'm just going to copy one of these and change it to the left bumper. And then that's all we need for the operator instructions so that we can read the different inputs from our controller to drive the robot around manually. Now that that's done, we can actually create our command. So let's create this command we're going to call tele op. So first, of course, import the package. And we're going to extend the command base. Now I'm going to bring in some constants here. So what these constants are the joystick inputs we're going to assign to a global variable. Then we have some ramp variables and some motor variables. The ramping is just to allow for the controller to have a nice steady ramp up and steady ramp down. So it's not a constant, and we get rid of that jerk movement. We need a constructor. Now we can't put anything in here right now because we haven't created the robot container yet. So I'm going to leave that blank. We'll put a to-do here. All right. Now we have to add the 4 main functions of the command-based structure. So put in okay, so let's go over these 4 methods. The first one is initializer. This is called when the command is called for the first time. So anything you want to initialize in here, such as resetting encoder values, resetting the yaw, things like that. Execute is called every time the command is run. So when it loops back that 20 millisecond loop that the robot has, it will call this execute function. End is called if the loop finishes or the command finishes. So if is finished returns true, or there is an interruption such as something went wrong and crashed the robot, the end will be called to end everything. I'm going to leave this all blank for now as we need to go and create the robot container so that we can start merging all the code together. Let's hop over to here. I'm just gonna delete all this because we don't need that. That can go. This can go. That can go. Just gonna comment this out for now. We will get to that later. All right. So first things first is that put this where it's supposed to be. All right, so we're going to import some of our classes now. So, Now, the reason why we have to bring it in here is the robot container is exactly what it sounds like. It's a container. It holds all the instances of our subsystems so that when our commands call them, we're not actually creating more instances of our subsystem. We're just passing along and using the same instance of that subsystem. The reason we do this is you don't want to have two instances of the drive-based subsystem because then they're going to be overlapping one another when you try and send stuff, which is never a good idea. So in the constructor, we are going to actually create the instances of those subsystems. So drive base is equal to new drive base. OI is equal to new OI. It's that simple. Now we want to set the default command for our drive base. And the default command is going to be new teleop. Now you'll see here, teleop can't be resolved to type. That's because it needs to be imported. So let's click there, import it, good to go. So we'll save that. You'll notice there's an error in robot. That's okay, we'll get to that later. So let's close this. And now we can go to our teleop command, which you can see here. And we can import the two subsystems that we needed for our command. So what I've done here is I've passed that instance that the robot container is holding of drive base to my local declaration of drive base. So therefore, I'm not creating a new instance. So now I can fulfill this to-do that we had. And that to-do is simply just going to be add requirements, drive base. Simple. So at our initializer, let's reset the encoders for new. We drive base reset encoder. So when we call our teleop command, so when we hit enable in teleop mode, it's going to reset the encoders to 0. Execute is going to be a bit complicated. I'm going to just copy in some code and then we'll go over what that code does. So at the beginning of execute, we're going to actually grab the data from our joysticks and then assign it to our global variables here that will go through the ramp math and then output to the holonomic drive in our drive-based subsystem. If you notice, we invert the value of the y-axis on the joystick. That is because when you use, like the Cartesian coordinates normally, on a joystick, it's inverted like this. If you look at your right-hand rule, so your positive y is actually going towards you or downwards on the joystick. This is based way back on the old joystick controls that were used for planes, as when you pull back, you actually go up, and when you push down, you go down, right? Which is a forward motion, so you're actually going down on your tip. And they never changed that from when they created the controllers. So if your y-axis on the controller is always negative, and the back axis is positive. So we invert that y-axis, so when we're driving, we can do the math. As we always, in mathematical terms, we want the y-axis to be positive in the forward direction and negative in the backwards direction. And if you remember, for a holonomic drive, we're looking for an x, y, and z. The x will be our left joystick x-axis. Our y will be our left joystick y-axis. And our z will be the right joystick's x-axis. If this command were to ever end, we would want to tell the motors to stop. So what we're going to do is drive base dot set drive motor speeds, and we're just going to make it 0 for everything. Therefore, if it ever ends, it just stops the motor. Then is finished is false because we always want this command to be running while we're in teleop mode. And that's it for the teleop drive base command. Next, we're going to add the object management system subsystem. So to do that, let's create another subsystem. New file. We're going to call this one oms.java. This one's going to be just as easy as before. So import the package. Create the class. We're going to have to define our motors. So in this case, and then we also have a servo motor. So we want to make sure to import the servo from the Studica library and not the WPI library. That's because our servo has an extended range from a default servo. So we have to remap that in our library. I'm just going to call it one claw. Yeah. And then for our sensors, we have the encoder on the elevator. And then I want to send my elevator encoder value to the shuffleboard. So I'm going to create a shuffleboard instance here. And we only have one network table entry, and that's just for the encoder value. Now we can create the constructor for our object management system. So here we've created the elevator motor instance and the servo motor instance, which I attached to PWM0 if we remember correct. Whoops, I'll change that. All right, and here we've created the Titan quad encoder. So let's create the methods for the rest here. I'm just going to copy it in to make it easier. So the first method we have here is we're going to set the elevator motor speed. Then we have the elevator encoder distance, and we have the servo position. In this case, we're going to set the servo angle based on degrees. So our servos have a range of 0 to 300 degrees, or plus or minus 150. The way that it's done on the VS Code side is that 0 is your minus 150 and 300 is your plus 150. So that range equates to 0 to 300. So if you wanted your robot to be in the middle, then you'd use 150 degrees to do that. Then we want to reset the encoders if ever called. And then in our periodic loop, we are going to update our encoder value. And that's it for the OMS subsystem. Now we're going to go to the container here and bring that OMS in. Save that. Now we're going to create another command to control just our object management system. So we're going to bring in our OMS and OI. So here is where the robot container really comes into play. Because the teleop command and the teleop OMS command will be running at the exact same time, both of them are using the same instance of OI. Now, if we had two instances of OI, that means we have two pairs of code running at the same time. Where we don't need that, we only actually need one instance running, and we pull off both that instance to handle both commands. So now our input from the controller is just a simple Boolean. So up, down, create a constructor. So in our initialize here, so over we're going to reset our elevator encoder. So in our execute, it's just going to be a simple like read of some Boolean values from the joysticks. So we're going to get controller inputs. So up is equal to oi.get. And then we're going to end it with some if statements. If up. I don't want to go too fast, so we'll just make it 50% speed. Then for the claw, if open. So I've already measured my servo for the differential that when open, it's at 150 degrees, and when closed, it's at 0 degrees. So we can end that on this. And we're going to add that to our robot container here, where we do ons.set default command. We say new teleup ons. It's not imported yet, so we'll just import it and we're good to go. So one last thing we want to go over in our programming is the autonomous code. To do the autonomous code, we're first going to create an auto folder. So in this commands, we're going to create a new folder. We're going to call it auto. Inside auto, create a new file called auto command.jet. This will act as our command that we send our autonomous commands to, as this contains the command group that allows us to just buffer and channel multiple commands together to send. So first things first is we have to add the package. Abstract. Sequential command. Now we're going to stack our inputs or methods. Import here. And that's it for this. We don't actually ever put any more code in here. It's just meant so that we can create huge lists of commands to send to the command organizer and groups structure. So once the auto command's done, we have to create some drive commands for our drive to work. So let's do that. New folder, drive commands. Try not to put space. So the new file we're going to call is, let's just call this one simple drive. So in simple drive.java, we're going to import our package. Okay, so we're going to take our drivetrain from our robot container. Okay, so what we've done here is we've created some global variables that are local, and we create a constructor where we take in the X, Y, and Z that we'll be sending to simple drive. This way we can tell which way we want the motor to move. I'll just copy the rest of the code because it's very simple. So we're not initializing anything as we're simply just driving. There's no sensor input or anything. In execute, we're just sending the X, Y, Z. And then if it ever ends, we're putting 0. And we're not putting a end condition here as we'll be using a timeout. And I will show you how to do that now. So in the auto folder, we're going to create a new file and we're going to call it just drive forward. In drive forward, so let's first import the package. I'm going to call public So I'm going to call a new simple drive for my command. Now I want to only move forward. So I'm not going to use the x-axis and I'm not going to use the z-axis. I'm only going to use the y-axis. So let's move forward at a speed of 50%, so 0.5. And like right now, this code will run forever. If I call drive forward, it will run forever until I hit disable. But I don't want that to happen. I want there to be a timeout. I'm going to hit dot with timeout. And then I'm going to put 5 seconds. So therefore, when I start this command, it will run forward. We'll call this simple drive, which is going in the Y direction. For 5 seconds, when it hits that 5 seconds, it just stops. It's done. The robot will no longer move. Because with the timeout, what it will do is when it times out, it will call this end function. In that end function, we have set drive motor speeds to 0, and it will stop the motors. That's it. That's how simple autonomous is. We call this function, and now it'll do it. However, we want to do some more advanced ones to show the differences between the different autonomous. So let's create another drive command here. So we're going to call this one drive with PID. Derek's head goes PID. So our PID class is going to be a little bit more complicated.
Proportional integral.
I'm going to copy my drive, simple drive, as it makes it a nice starting point. Use the P. Drive with PID. And PID. So now when we look at it, we're actually going to change our inputs a little different here. So we no longer have X, Y, Z. We're now going to have a set point distances that we want our drive to go to. So we have a distance that we want to go. And we want a angle. I'm just going to call it yaw. So in our constructor, we need those values. So in this case, it's going to be a double set point distance. I'll explain the epsilon after. Okay. Let's also create the PID controller. Oh, did I import the wrong one? I did, yeah. Yeah. So we're going to be doing two PIDs here. We're going to have the y-axis, which controls our forward and back movement. And then we're also going to have the z-axis. The z-axis will be tied to our navx, and this will control the angle that we drive at. As we want our robot to stay driving in a straight line, that's why we want this. So the z-axis will control if it drives in a straight line or not. So by having the two PIDs, we can mesh them together so we can drive forward and at a 0-degree angle for that forward heading.
Right. So it's important when you're doing this code for this PID, and you got to remember this, is that's why in this robot design, the VMX is centered in on the top of the robot. And remember, we talked about the front of the robot is where the OMS is, the object management system. So the default orientation for the integrated motion unit is the front of the robot matches the direction where that Studica logo is on the front of that VMX, which is your Y, okay? So if you mount your VMX somewhere else and try to run this code, you're not going to get the right data. You're going to have to reorient everything, okay? So remember, that's why that's there, because the default forward axis on the IMU is the Y axis, and that's why this is mounted flat and in this top center of the robot, right? So that's what's going to straighten it this way, or that's what's going to give it the forward motion, and then the Z axis with the right hand rule is up. So that's what we're using, okay, for the rotation.
Okay. So we're going to say this support distance. So in our, we also have to add a whole bunch of other things, such as defining the PIDs, so PID y-axis equal to new PID controller. So in here, this is where you set your KP, KI, and KD. For our y-axis, I'm just going to use a simple 1. So I'm only really doing a P controller. Okay. So the reason for the epsilon for the distance and the yaw. The epsilon is the tolerance that you want to have your PID go to. For example, if I set my set point distance to 1,000 millimeters, so 1 meter, and I want my epsilon distance to be like, say, 10 millimeters, that means I'm giving myself 10 millimeters of plus or 10 millimeters of minus accuracy for that PID to hit. You can tune your PID controller and decrease your epsilon distance as you go so that your robot becomes more and more accurate. And I need a PID for my Z-axis. Okay. So in my initialize, I want to make sure that I reset everything. So I'm going to reset my encoders. I'm going to reset. I'm going to reset my encoders. I'm going to reset the yaw, and I'm going to reset the PID controllers that they start at 0, so that the error is not accumulating. In my execute, it's going to get a little bit more complicated. So my X, because we're not doing anything on the X, I'm just going to put 0.0 because we don't want any X translation. For the Y-axis, I'm going to create a clamp to set it to specific what I want. So I'm going to use the math util library. Clamp. Okay, so let's go over what's happening here. So on my y-axis, I'm using the y-axis PID calculation. And on the z-axis, I'm using the z-axis PID. What the clamp is doing is it's clamping the output from the PID calculation to a range of minus 0.5 to 0.5. So that means I only want my to drive forward or backwards at a max of 50%. For my yaw axis on the z-axis, I'm putting it at 100%. The reason I want this is I want to really make sure that I'm driving in a straight line. So it's going to put more oomph into turning to make sure that it's correct. And I'm using my average distance here as I want to get the distance from the left motor and the right motor and mesh them together so that I have a very good forward distance track. Now, we actually want this command to finish when we hit the set point and not based on an interrupt. So what we have to do is instead of return false, we're just going to do we're going to base this on driving forward a set distance, not on the angle. So our y-axis dot at set point. So what this will do is when our y-axis PID hits its set point, it's going to tell the command, hey, I'm finished, stop running. And that's all it's going to do. And we can now save that. Now, if we remember back to our drive forward, it's just like this. However, now we want to drive forward with PID. So we're going to do something similar. So I'm going to create in the auto folder a new file, drive forward with PID. Let's copy this code over as it's listed. Now, instead of using simple drive, we're going to use different. So I'm going to say new drive with PID. You can see here's our inputs that we need. So our set point distance, let's say we want to drive 1 meter forward, is 1,000 millimeters as the encoders respond in millimeters. Our epsilon distance is 10 because we only really need a 10 millimeter tolerance because anything more than that or less than that's really accurate. And I didn't really tune the PID, so I'm not going to get better than that. And then, of course, for our yaw, we want a 0 degree heading. And our epsilon, let's say we want a 1 degree accuracy. And it's as simple as that. Now, I know that this PID is going to roughly take about 3 seconds to run. So I'm going to add a timeout of 5 seconds. The reason why I'm adding a timeout here is that if I had a command that was going to run after this drive with PID command, so let me show you an example here. So if I was going to do new wait command, and I was going to copy this. So what happened here now is that when this command, I'm going to drive forward for 1,000 millimeters, stop for 1 second, and then drive backwards for 1,000 millimeters. You know what happens if there was no timeout here and something went wrong where the encoders wasn't being read? This command would run forever, or if this command didn't stop on time, it would actually never go to the next command in line because there's nothing there telling the command to end. So the back system is just going to be hung on that command and never move forward. So by adding the timeout, I know that if something ever happens in this command, that after 5 seconds, it will just move on and do the task what's required. So it's something to keep in mind. Always have a timeout there just in case something happens. However, we're just going to drive forward, so I'm going to delete this. So that we essentially now have all the base code done. We just need to adjust some other things so that we can select what command we want to run and how to do that. Let's go back to the robot container first, where we're going to do some coding. So in robot container, we're going to add a few things first. So underneath our objects here for everything else, we're going to add 2 more objects. So what the sendable chooser is, it's a function on the shuffleboard that allows us to choose what autonomous command we want to run when we start our autonomous. Now, of course, you don't need to do this. There are other ways to do it, but this is just a cool way to do it so that I can easily add as many autonomouses as I want and make sure I choose the right one in my code. So now in our autonomous command, we can uncomment this now. So now instead of returning this, instead of just returning this blank command that has nothing in it, we're going to return something else. So I need this to go there. So what I've done here is that we are going to grab from the auto chooser in the shuffleboard the selected mode that we want. Now what happens is if the getter doesn't work or it's blank, it's going to default to our drive forward command so that there's always something there. Now we can just create a blank command for our default so that if it doesn't actually get what command we want to run, it just doesn't run any autonomous. But I'm just going to put that there as we know that it will be able to get. So now we'll save that and we're done in the robot container. Now, in robot, we're going to add some more code. So to start, we're going to do most of our code inside the disabled area. So we're going to find the disabled. So here we have the robot init, the robot periodic, and then here's the disabled. So first things first, we're going to check if the robot container auto chooser is blank. So what we've done is, if it's blank, we're going to create a new sendable chooser. Okay, so now we simply put that if our drive forward command on the smart dashboard with the default option already chosen to be drive forward. However, I want to add my drive forward with PID as well. So I'm going to create a simple function here that I can call repeatedly so that I don't have to have this huge block of code every time I want to add a new autonomous function. So public. Oops. Okay, so when I call this function, this method, and I add the parameters, I can add my autonomous options to the chooser for it to be selected. So before I send the chooser to the smart dashboard, I want to add all my autonomous functions. So let's add the drive forward with PID right now. So we're going to add auto mode. So we're going to have to send the chooser in first. So that's robot container.auto chooser. Our auto is going to be drive forward with PID. And our command is going to be a new drive forward with PID. And I need to import this. And there you go. And that's simply it. That's all that's required to program and move this whole robot. Now I'm going to get rid of these old example projects and example commands that we just don't need. So I think that might keep me up here. So we're going to take a break right now. We're going to set up the robot on the court, and we're going to show you the robot driving around first using the X, Y, and Z input. And then we're going to show you the autonomous of the robot driving with the drive forward command, and then the robot driving with the PID command. Hi everyone, we're back again. So hopefully you can all hear me and we're good to go. So the robot is now on the field. Hopefully you can all see the robot driving around. I'm gonna just quickly share my screen here so you guys can see the control station console with the shuffleboard. So let me share my screen here again. So here I have the control station console. I'm connected to my robot. On the shuffleboard, you can see the values that we outputted. On the smart dashboard, here you can see the sendable chooser. So notice how this is on the smart dashboard, where everything else we put on the training robot tab. So on the smart dashboard, you can see the sendable chooser. So we can see the two commands that we created. So it was the drive forward and the drive forward with PID. The chosen auto mode here just shows you which one you selected so that you know that you selected the right one. So let's show you the robot driving around first. So if I hit enable here by hitting E, you can see that it reset the encoder values, but not the yaw, as I did not want the yaw to be reset. If I start driving the robot around, you can see the encoder values change. And it's real time, which shows, and these encoders are plugged into the Titan and are using the latest libraries that we posted yesterday. All right, it's as simple as that. So I'm now going to go back so you guys can see the robot. Get it enabled. So when I move the joystick in the forward direction, so the left joystick, you can see the robot drives forward. When I go in the back direction, it drives backwards. If I do the X direction on the right joystick, which is what we made for the Z axis, you can see that it just rotates. If I use the X axis on the joystick, I can drive in a forward motion. In a sideways motion. Right? I can close the claw by pressing the right bumper. You can see the claw opening and closing. I can move the elevator up and down by hitting the right bumper or the right trigger to go up or down on the robot. So here you can see it going up and down. Sorry, my joystick has some drift that I need to adjust the everything. So let's show you the drive commands. So I'm going to stop the robot right about there. Let's save. So let's share the screen again. So I'm going to go to the smart dashboard. I'm going to choose the drive forward command, which you remember was just to drive forward for 5 seconds. And then it's going to stop. So in the command, the console, to switch to autonomous mode, I'm going to hit, as you can see here, A. You can see now it shows autonomous mode. I'm actually going to move the robot a little bit farther backwards. I'm going to switch back to operator mode by hitting O. So I'll put the robot about there. All right. So now I'm going to switch back to the main screen so you guys can see. I'm not going to enable the robot in autonomous mode so that you guys can see it drive forward. So you can see it's driving forward in autonomous for 5 seconds and it stopped. Now I'm going to share my screen so you can see that I'm going to do that again, but share my screen with the video in the background so you guys can see it working. So let's put the robot back in its spot. Right? So we're on the sendable chooser, drive forward, switch to autonomous mode. Now I'm gonna hit enable. You see it's autonomous is enabled, the robot's driving forward, and it stops. Now if you notice, the autonomous is still enabled, but it's not running that command again because we only wanted the command to run for that timeout period. If I took that timeout out, that robot would still be driving forward, crash through, then drive into Derek's CNC machine, and he'd be very mad.
Right. So just a quick point about this for some people that use the old control system, so that you understand now. What's happening here with the driver console is that robot right now is in another room from us. It's I don't know, 30, 40 feet away, so 10 meters, 15 meters away for metric. And we are just direct connected to the controller via the driver console on the PC. So when you're in teleoperated mode, you can test, you can run, you can do different aspects. And then you'll notice that when you enable autonomous, okay, if the code is running on the robot, it will run whatever autonomous code you have chosen here. So you can have multiple autonomous code, but in this case, you're running, I can't see the name of it anymore, whatever you've got.
Drive forward.
He's running drive forward. So he's chosen drive forward. He hits enable. And when he does that, that robot will start, okay? And if you don't like it, you can sit here and stop. So technically you wouldn't need to run out and hit that emergency stop on the robot anymore if you didn't want to.
Oh, here, I can show it.
Right?
So
you'll be able to do everything from the driver console here.
So if I hit enable now, you can see the robot start going. If I hit disable by hitting D, it just stops because of all the safety features that we got.
Right. So this is a safety feature that was added with the driver console. Okay, the ability to start and stop your robot remotely, okay, at any time, so you wouldn't need to run out onto the court. And that is the driver console that's posted, and that's how you'll enable and disable and control the robot right now. Okay.
So now we're gonna show the drive forward with PID. I'm trying to line the robot as best as I can up with the white
line,
so you guys can see it. Okay. So if I share my screen, you can see that we're going to now choose drive forward with PID, right? So we're driving forward with PID, and then I'm going to enable it. I'm going to show you it first on the live camera, and then I'll switch to here where you can see it. Right.
Want me to kick it?
No. So right now I'm going to hit enable. Oops. Choose focus. You'll see it drive forward. It's nice and straight. And when it reaches that 1 meter distance, it will stop. So let's show it now on the console. But let me first drive the robot backwards. I'm driving in another room with no line of sight, using a screen from the camera that we're using to show you this. All right. Okay, so let's share a screen so you guys can see it on this side. So drive with PID, and I'm going to show you the values here so you can see how accurate it is. All right. So let's switch to autonomous mode. Now I'm going to enable it. There it's going. Stop. So you can see our yaw value was within that 1 degree that we wanted. Our left encoder hit 1007. Our right encoder hit 1007. So it was within the 10 millimeter epsilon value that we gave it for stopping, which is what we wanted. So I don't know if Derek wants to go out there. I'm going to enable the robot, and he's going to push it a little bit, and you'll see that the robot will correct.
Yeah, I got George here.
Yeah. Wait, I'm gonna change the.
Well, I was pushing on that pretty hard, and it would not let me kick that. No, it would just keep it straight each way, and I was really giving that a shot. So
Yeah, so hopefully this has given you guys a good explanation to show how easy it is to use the PID and to mesh it like that, especially for when driving the robot forward. As you saw there, Derek really struggled to move that robot based on how strong it was trying to keep that PID on that 1 degree of freedom, right? That we set for it on the epsilon value. If you had any questions right now, please ask it now, and hopefully I'll be able to show it for you guys if you wanted me to show you any. Other than that, I'll keep driving the robot around in the video so that you guys can see it drive and do things. So someone has asked a question in the how do I transfer code to the VMX? I will show that to you right now. All right. Let me drag this over to the right screen. All right, just let me share my screen here so you guys can see. So to transfer the code over to the VMX, first things first is you have to be connected to the VMX via Wi-Fi or Ethernet. It's up to you, but it is preferred to be connected to the VMX via the Wi-Fi connection, so the access point. You want to make sure that your target is set to the VMX, so you can hit the VMX Pi, or if you have the blue version for the WorldSkills one, you want to make sure that you have changed the deployed target to VMX Pi. I will show it here quickly just to show you. And what that does is in the build.gradle, it configures it for the VMX instead of another target. Now, when I want to deploy to the robot, I make sure that I am connected and I hit deploy robot code. And you'll see here in the terminal that it starts deploying to the VMX. And it's now deployed, and I have the real log that pops up. And with code deployed, I can easily start driving the robot around again. So someone asked, where is the encoder used in the code? I'm going to show that again on my screen so that you guys can see it. So there are a couple places the encoders are used. For example, in the PID, we use it here to as our process variable. Then in the drivetrain itself, so if we look here, we first initialize the encoders up here. We then create the instances of the encoder here. Then we read the value of the encoders based on when they're called. Here we grab the average encoder distance. And here we're just outputting the encoders to the periodic output, which is the shuffleboard. Again, all this code is already being posted to our example GitHub. Let me grab it for you so you guys can see where it's located. So on our WorldSkills example projects GitHub, you will find all the code that we've done for previous examples and tutorials. Inside the training robot, you will find all the code that we did today and what is currently running on the robot. So if you look inside the source, you will find the subsystems that we did along with the commands such as the drive with PID will all be in here for you to download and use yourself. then we're on you.
Are we saying
Yeah.
goodbye to everyone?
Yeah.
And the camera's right here in front of me?
Yeah.
All right.
We're on you.
Hi, everyone. Just can't see anybody right now, but I just wanted to say thank you, and I hope you enjoyed the training. We certainly, I think everybody, I've had some feedback, and a lot of people do enjoy it. I hope you got a lot out of it, and you're able to move on to the next step. I know Derek talked about the online competition and moving along. I'm going to actually work on showing who's already registered. We already received 3 teams that have already gone through their national competitions and have registered with us. So, I hope that you guys all have everything ready. We have that deadline of the 14th. And so I look forward to getting everybody's registration in, and look forward to doing this again. If you have any suggestions, ideas, please always let us know. We're here to help. And I hope this has been, enjoyable as well as helpful for everyone. Have a great rest of the day. I know it's late for some of you, and we'll talk to you soon. Thank you. Bye-bye. Bye-bye. Now there's Derek.
Making notes, taking names. What do you say?